have T equals ASFY. There is a requirement. This is maximum reinforcement requirement. So ACI tells us that the beam is to be designed to have at least a strain of how much? Say that again. I can't hear you. Is it 002? No. 005? 004. Very good. That's what I wanted to hear. 004. That's the reference for maximum. Yeah. For maximum reinforcement, that's 004. So when I draw the strain diagram, this is 0.004. And that's equal to how much? The strain at the top is 0.003. Okay? So based on that, you can define a C that will be the maximum C. Maximum C you can use in your beam design. This will be the max. Anything below that will reduce your epsilon T. Therefore, less than C corresponding to 0.003 and 0.004 strains is acceptable. But C cannot be greater than what we have here. So if you plug in the numbers, you will see, depending on the steel grade you are using, for a 60 grade steel, that's 415 MPa steel, you can say epsilon Y is 0.002. So based on that, you can find out AS max. All that I've done, I mean, I'm not going into all the details, but from the strain diagram, this is 0.003. So let's, okay, maybe I could just draw a simple figure that will make it clear. So this is 0.004. So this is 0.003. So this depth is dt. Okay, so if I extend this from here to here is 0.007. This is 0.003. So this is 0.003 plus 0.004 is 0.007. So based on that, you can find out C over dt. Maximum value is 0.003 over 0.003 plus 0.004. So this will work out to be how much? 3 over 7. Right? 3 over 7. So that's all. It's such a simple approach. Now, with that, we can always find out the AS max, which is equal to the corresponding depth of 3 over 7. So C equals, maximum C is 3 over 7 times dt. That's our maximum. So find out the corresponding compressive force, corresponding tensile force, rearrange the terms, and you get AS max equals 0.85 beta 1 F prime C over Fy 3 over 7 B times dt. So as long as you use consistent units, these are two similar quantities. Beta 1 has no units. 3 over 7 is just a fractional value. If you use millimeter here, that will be AS max in millimeter. Okay, very simple. Alright, so we'll go over this example again. The data is the same. We have width B is 250 millimeter, H is 350 millimeter, H total depth, overall depth, and the effective depth is 310 millimeter, and M25 grade concrete is sigma CK is 25 MPa, steel 415 MPa, area of steel 339 square millimeter, beam span 5 meters, and then we have, let's use ACI to find out the factor load moment based on WD of 3.7 and live load of 3.75. So just use the same data. Now our factors are, I made a mistake here. I think it's 1.2 and 1.6. So that should give me 11 point something, 49 or something. But anyway, let me see. That's a little small mistake. It's a major mistake actually. Let's see. Let's go to this. We'll get this number later. It's the, now depth of the compression block can be based on ASFY over 0.85 F prime C times B. So that works out to be 26.48 millimeter. If you compare it with what we had in IS 456, that was much larger. Then moment arm is 296.8, and then total compressive force is 140.7, tensile force is 140.7. Now moment strength is 41.75, but remember we also need to use a phi factor there. So and also FCK is not same as F prime C. Beta 1 is 0.85 because F prime C is less than 27.58. So C equals 31.15. So if you have your slides, you can follow this quite easily. And then you need to find out epsilon Ty, which is 0.002 approximately for 415 MPa steel. Epsilon T is 0.002686. It's greater than 0.005. How do I get epsilon T? I get epsilon T based on strain diagram. So strain diagram gives you epsilon T of 0.02686, which is greater than 0.005. But what's the significance of 0.005? That's tension controlled condition, right? That means phi factor is 0.9. That's what I get here. So that would be 0.9. 0.9 times 41.75 is 37.58. So the required strength, of course this is not correct because I have used the wrong numbers. If you have a calculator, you can give me the numbers. I can give. It's 1.2 times 3.7 plus 1.6 times 3.75. That's your, how much? Okay, so moment is oops. How much is that? 32.
Yeah.
Oh, 32. Wow, 32. Okay. Now our ratio is, oh wow, even more. Yes, that's right. That's okay. Wow, that's really big difference. I did this in the middle of the night, last night or the day before that. So sorry about the mistake. 37.58 is what we have. Required strength. This one is 37.58. Very good. Okay. The difference is much more than what I thought. So for the same loads, we are having how much? What's this ratio? 1.15. Wow, that's a lot of difference. 15% difference. It's more than 1.07. So please make this correction. I'll correct it right away, which is no problem. But okay. So the difference is a lot, right? You see that? There is a lot of difference between. Do you see what I'm trying to highlight? We can reduce what? Yeah, I know. But what I'm saying is, if you are designing the same section using IS 456 and ACI 318 with the same loads, same service loads, we are able to use moment strength, which is the moment strength of the same section is 15% more than what we need from IS 456. That's what I'm trying to say. There is such a big difference. Okay? All right. Now we need to use AS min equation, and this is in SI units, 0.25 square root of F prime C Fy. I converted that into SI units. So that works out, minimum is 233 square millimeter by one equation. The other equation gives me 258 millimeter. So which one do you pick, the smaller or larger? Larger for sure, so that's what governs, 258. What about AS max? AS max, we have this expression, plug in the numbers, and you get 1446 square inch, which is definitely greater than 339. So our 339 provided is smaller than the maximum, larger than the minimum, therefore it's in good range. All right, so that's how much we have for introduction to ACI method.